Welcome back. Here I want to prove the matrix inverse algorithm that we talked about in the last video, and to do it we're going to use something called elementary matrices. But before getting into that, let me remind you that what the algorithm said. It just said that if A is an invertible matrix, then the way the algorithm worked is we put A and the identity into a matrix together, and we would be able to row reduce so that we ended up with the identity and the inverse matrix. And that was the algorithm. So you set up this augmented matrix, you row reduce until you see the identity here, and the remaining portion is the inverse. So the goal of this video is to prove that's true. And the way we're going to prove it is by using elementary matrices, which we will talk about first. So an elementary matrix, it's any matrix that can be obtained by performing a single row operation on the identity. So you start with the identity, you perform one row operation, and the resulting matrix is called an elementary matrix. So for example here's a 3 by 3 identity matrix. If I swap the first two rows, row 1 and row 2, I get this matrix. This is an example of an elementary matrix. Second row operation, I can of course multiply a row by a scalar. So if I multiply the first row by 2, I get this elementary matrix. I can also do replacement. Maybe I replace row 3 by 2 times row 1 plus row 3. I get another elementary matrix. So let's see why these elementary matrices are useful, and we're going to do it with an example. So let A be Rob's favorite matrix. And what I want to do is I want to multiply that matrix by these elementary matrices that I have over here. So I want to start with E1. If I multiply this by A and I do it on the left, well, give it a shot. Just do the multiplication quickly. You can pause the video if you want to give yourself some time to do it. But what ends up happening is I get this matrix. I'm just going to give it the answer. And if I look at the original matrix, all I ended up doing was swapping the first two rows. And that's really interesting because E1, this elementary matrix, was obtained by swapping the first two rows of the identity. So multiplication by E1, what it did here is it swapped R1 and R2. And again, that's exactly how E1 was obtained. If we do E2 times A, again, give it a shot. Multiply this by this matrix A here. What do you get? Well, I'm just going to give you the answer again. You get 2, 4, 6, 4, 5, 6, 7, 8, 9. And if you compare this to the original matrix, all that happened is we multiplied the first row by 2. So here we multiplied R1 by 2. And again, let's look at this E2. This E2 was obtained by multiplying the first row of the identity by 2. So there's something really interesting going on here. And let's do the last one. If I do E3 times A, well, maybe you can guess what's going to happen here. Because each of these products that I did, I ended up doing the row operation associated to these elementary matrices. And the same thing will happen here. When I do this product, what will end up happening is I'm going to replace row 3 with 2 times row 1 plus row 3. And again, I suggest actually multiply it out yourself to see this is true, but the third row will end up being a 9, 12, and 15. And this is obtained by replacing row 3 by 2 row 1 plus row 3. So you do these examples and you see that if you multiply on the left side by an elementary matrix, you end up doing one of these simple row operations. And the row operation you do is the row operation used to obtain those elementary matrices. So this is true in general. If you take any elementary matrix, then first off, it corresponds to a row operation. If I go back to this example, this elementary matrix we obtained by doing this row operation. So every elementary matrix corresponds to a row operation. And so if I take that elementary matrix and multiply it on the left to some other matrix, A, then this new matrix that I get is obtained by performing that row operation to A. And so that's just a general fact. And this is going to be what we use to prove the algorithm for finding the inverse of a matrix. One last thing to note before getting to the proof of the algorithm is that if E is any elementary matrix, then it is automatically invertible. And to prove this, it comes down to thinking of the three kinds of elementary matrices you can have. You can have an elementary matrix corresponding to multiplying a row by a scalar. You can have one corresponding to swapping two rows, or you can have one corresponding to replacing a row by the sum of itself with a multiple of another row. So just the three row operations. And I'm not going to go through the proof of every single one, but I do just want to go through one case. I want to show that if we have an elementary matrix corresponding to multiplying a row by a scalar, then it is invertible. And to do it, we just have to show that it has an inverse. So we're just going to produce another matrix that when we multiply them together, we get the identity. And so we'll start there. Let's say E is an elementary matrix, and I want it to be one that corresponds to multiplying the ith row by n. So n is any integer, or any real number rather, and I is just one of the rows in your matrix. So if it's a 3 by 3 matrix, maybe I'm choosing the second row and I'm multiplying it by 5. Now I want to take another elementary matrix F, and this is going to correspond to multiplying the same row by 1 over n. And now let's see what happens if I multiply these two matrices. If I do E times F times the identity, let's think about what happens. First, multiplying by F by the identity, that corresponds to multiplying the ith row by 1 over n. So what I did is I just multiplied the ith row by 1 over n. And then I multiplied by E, which says multiply the ith row by n. So I multiply by 1 over n, then I multiply by n. Obviously, those cancel out and give me 1. So I'm just left with the identity again after that. Similarly, if I do F times E times the identity, I'll just get the identity again, because I multiply by n first, then I multiply by 1 over n, and they cancel each other out. And so here, in these equations, of course, this identity doesn't really matter. This is just the same thing as E times F. So this says E times F is the identity, and F times E is also the identity. That means E is invertible. It has an inverse. So that's how you show that any elementary matrix corresponding to multiplying a row is by a number is invertible. And I leave it to you to think about the other two cases. If you swap two rows, can you think about the inverse of that elementary matrix? And what if you do a replacement? Can you think of what that inverse would be? Here we are. We're finally at the proof of the algorithm for producing the inverse of a matrix. And so to start, let's say A is invertible, and we want to show that that algorithm is true that we talked about. And so the first thing that we can say right away, and this we proved in the last video, is that if A is invertible, then it's row equivalent to the identity, meaning you can perform row operations on A to end up getting the identity. When you put A in reduced echelon form, it is the identity. And these row operations correspond to elementary matrices. So another way to say that is that we can multiply A by elementary matrices and get the identity. So then there are elementary matrices, which I'll call E1 to EP, corresponding to row operations. And these are the row operations that reduce A to I. And these matrices satisfy the equation, or maybe this identity. When I multiply A by these matrices, I get the identity. And now the rest of the proof is just algebraically manipulating this equation until we see what we need to see, until we get to the punchline. And so the first point here I want to make or remind you is that all of these elementary matrices are invertible. And so that means that the entire product is invertible. That was a property that we saw in the past. So let me multiply both sides by the inverse of that product, which I could definitely do. Then here I have a matrix times its inverse, so this becomes the identity. These just go away. And here, well, that's just itself. So I can say A equals the inverse of the product of these elementary matrices. Now the next thing I want to do is take the inverse of both sides, which I could do because I know A is invertible, and of course this is invertible. So when I do that, I get A inverse equals the inverse of this product inverse. And we know from another property that when you take the inverse of an inverse, you just get the original thing back. So that tells me that A inverse is the same thing as the product of these elementary matrices, and I'm going to stick on the identity at the end. This doesn't really add anything to it it doesn't change the matrix at all. Of course, I just multiply it by the identity, I get the same thing back. But putting it here illustrates the punchline now, because A inverse can be obtained from the identity by multiplying by these elementary matrices. So A inverse is obtained by performing row operations, and these are the row operations corresponding to the EI to EP, corresponding to the elementary matrices. So you can get the inverse by performing these row operations on the identity, rather. And now if we look back, these elementary matrices, these were the matrices that I multiplied A by to get the identity. So these row operations that I perform on the identity to get the inverse, they were the same exact row operations I performed on A to get the inverse. In other words, if I look at this matrix, A with the identity in here, and I row reduce this thing, I can use these same exact row operations across the board, and I'm able to turn A into the identity, and at the same time I'm able to turn the identity into A inverse. And that's our algorithm. That's all it takes. So once we had this machinery of elementary matrices, it was pretty simple to prove this algorithm.